I think my screen is visible to everyone. I am actually sharing my screen where you can see a 2 degree of freedom system which already we have analyzed. Okay, so this is the linear 2 degree freedom system where we actually last classes we were able to find out the two natural frequencies of the system. Okay, and finally we found out the two mode shapes. Okay, so this one is the principal mode shape. This is the ratio between the steady state amplitude of the two masses x1, capital X1 by capital X2, and the first principal mode of vibration, it was +1. Okay, and the second principal mode of vibration, that is x1 by x2, this suffix is 2. Okay, principal mode of vibration, this was the mode shape. Okay, mode shape, shape, mode shape, it is -1. Okay, and what was their actually physical meaning? This +1 means, so when the masses, okay, when the first mass is displaced in a downward direction with an amplitude of x1, okay, the second mass will also displaced in the downward, okay, in the same direction. So that is why it is +1. And here this negative sign actually represents that when the mass m1 is displaced in the downward direction, at the same time the mass m2 will be displaced in the upward direction. Okay, so those things are written here. So one thing is that, so you can give unequal displacement to the two masses. Okay, so there are different cases. So here actually we are assuming that we are giving the equal displacement to the two masses. Okay, so then these things will happen. Okay, on both the cases, in both the cases, that is principal modes of vibration cases. So this is the case for linear 2 degree freedom system. So today we are going to study, so what will be the behavior of the system, or what will be the principal mode of vibration, as well as what will be the frequencies of the system for a 2 degree rotor system. Okay, so yes, so here you can see a 2 degree rotor system. So here this is the projection of the rotors. So while you are projecting the rotors, so the small rotor, you will get a small rectangle. Okay, so whose moment of inertia, mass moment of inertia, let's take it is I1. And here after projecting, so you will get the 2D view of the second rotor, so where you will be seeing a bigger rotor, okay, at this end. So its mass moment of inertia is I2. Okay, so consider two rotor torsional system. So it will be a torsional system because the two discs are joined by a stiff rod of stiffness KT. Okay, so here I1 and I2 are the two respective moment of inertia of these two rotors. Kt is the torsional stiffness of the shaft. Okay, theta 1 and theta 2. Here you can see, if you just project these two, then you will get this top view. Okay, you can see that, you can say that this is the side view, or this is the if this is vertical, then you can see one top view like this one. Okay, so here it is a side view because it is on the right side. Okay, so you can see there are two twisting angles, one is theta 1, one is theta 2, because there are two rotors. Okay, so when you will be displacing these two rotors with an angle of theta 1 and theta 2, so these will be the two displacements of these two rotors at any instant. Okay, they are taken as positive in the clockwise direction and negative in the anti-clockwise direction. Okay, so here you can see in the positive clockwise direction they are twisted. Okay, and the relative, okay, and the relative twist on the shaft, because on this shaft you will get a relative twist, isn't it, due to this theta 1 and theta 2, you will get a
Excuse me,
relative
sir.
twist. And
I'm not sure if sir. I-text ko
just
status.
wait, just wait. Okay, Simanta has joined, but Manas, I think, yeah, tell him to join. Yes. Okay, so again I am just repeating the things because few of you have joined now. Just wait. Okay, in a nutshell I will be telling the things. straight. So here there is a 2-degree rotor system. Two discs are there. So these two discs are actually given this twisting angle or displacement, twisting displacement, that is theta1 and theta2 in the positive clockwise direction. Okay. So the stiff rod will be experiencing a relative twist, okay, theta2 minus theta1, because we will assume that this theta2 is greater than theta1. Okay, so here the stiff rod will be experiencing an relative displacement of theta2 minus theta1. Okay, so for the relative displacement of the two rotors, so shaft exerts a torque. So what will be the value of this torque? So kt into the displacement. So displacement will be the relative displacement. So kt into theta2 minus theta1 will be the torque which will be experienced by this shaft. Okay. Yes. Now let us consider the separation, okay, or this length of this stiff rod, it is L, okay, or separation of these two rotors are L. So if you just apply Newton's second law of motion, so you will get the differential equation for this two rotor system, isn't it? So directly we can write for this disk I1, okay, means M1, or you can say mass moment of inertia is I1. That is why for this disk having mass moment of inertia I1, so the Newton's second law of motion equation will be, so I1 theta1 double dot. So we have already done this type of actually exercise. So I1 theta1 double dot will be equals to kt theta2 minus theta1. Okay, so after rearrangements, so you will be writing this one. So k2 theta2 will be writing on the right hand side. Okay, and for this second disk, so it will be experiencing an opposite torque, isn't it? Because if it is twisting, so it will be just experiencing an torque, a torque which will be in the opposite direction. Okay, so I2 theta2 double dot will be minus of kt theta2 minus theta1, because this theta2 minus theta1 will be the relative displacements which will be experienced by this stiff rod. Okay, so after rearrangements of the second equation for the second I2 disk, so I2 theta2 double dot, okay, so don't write it is J2, okay, it is I2 only. So J actually generally written for this polar moment of inertia. Here it is the mass moment of inertia. So you may not see it distinctly, but you have to consider that this is I. So I2 theta2 double dot plus K2 theta2. Okay, from here you can write this one, and kt into theta1. So here it was theta2 and here it is theta1. Okay, now we need to actually we need to consider that the twisting of this rotor is sinusoidal, okay, or the simple harmonic motion, because we are actually analyzing the motion of this 2-degree freedom system, isn't it? Just wait if anyone is waiting or not. Okay, so here I think my screen is visible to everyone. Yes or no? Okay, so this theta1 will be equals to beta1 sine omega t, because in earlier case also for this 2-degree freedom system, you can see this one we have assumed as x1 equals to x1 sine omega t, where x1 is a steady state of vibration of amplitude of vibration, and here this x2 is equals to x2 sine omega t. So here also we need to assume this as beta1 sine omega t and beta2 sine omega t. Okay, this second displacement, and here you can notice this similarity of these two frequencies. Am I audible? Dear students, am I audible? Okay,
Yes,
my
sir.
screen is visible. Yes or no?
Yes.
Okay. Okay, so now what I will be doing, so I will be just differentiating this one with respect to t for 2 times. Okay, so I will be getting theta 1 double dot. Okay, and again I will be differentiating it with respect to t for twice. Okay, so theta 2 double dot I will get. So what I will be doing, I will be putting all those values in those equations, okay, separately. So I will be getting this equation, okay. So this is one homework for you, because every time I will not be able to show you, okay, each and every step. So from here, if you just double differentiate it and put it, okay, these values of theta 1 double dot and theta 1, okay, and theta 2, so you will get this type of equation, okay. Very simple thing, only you need to differentiate it twice, okay. The second equation also, from here, after putting the value of theta 2 double dot and theta 2, so you will be getting this equation. Already we have done it for translational vibratory motion, okay, for 2 degree of freedom system, what is actually I showed you in the last class, okay, in the last classes actually. Yeah, so now what I will be doing, I will be finding out the ratio just like the earlier case. So I will be finding out beta 1 minus beta 2. So what I will be getting, so kt, so this will come here, okay. So I will be getting this ratio. Then again from the second equation also I will be getting this ratio beta 1 by beta 2. So this one, okay, this value I will be getting. So here you can see this other part, okay. So this other part you just omit, okay. So these are nothing but calculations. So only this ratio and this ratio it is there for beta 1 by beta 2. This is from the first equation, this is from the second equation, means from the first equation, and this is from the second equation. So just you omit, okay, strike it out all those things. So while you will be actually preparing these notes, okay. So these are nothing but calculations. So while I was actually practicing, so here actually I wrote all those things, okay. You just omit all those things, just mark with some line, okay, while you are writing. So now what I can do, because these are the same ratio, so I can equate both of these equations. So on the right hand side I will be equating, so this equals to this, okay. So from here, after multiplication, so what I will be getting, so kt square minus, okay, so minus, so this multiplied by this, okay. So kt square minus, why minus is written, because this will be on the right hand side. So if you just carry it on the left hand side, so there will be minus, so this multiplied by this. So finally what you will be getting, so you will be getting one quadratic equation, okay. Not quadratic, so you will be getting this expression as omega square as common under bracket I1 I2 omega square minus kt, this one k1 plus I1 plus I2 equals to 0, bracket close, okay. So here I think it is not a distinct one. So when you will be practicing, so you will be come to know what that it is kt, and this is I1, and plus this is I2, okay. So from this equation actually, so you will be able to find out the value of this omega, isn't it? Because here it is omega square, so omega will be equals to 0. So first natural frequency, whatever you will be getting, it is as 0, okay. So the first natural frequency will be 0 for this 2-degree freedom rotor system, understood? Now for the second frequency, so what will be the natural frequency, second natural frequency? So from here directly you can find out. So this will be on the right hand side of this equation, because this will be equals to 0, okay. So as because omega n 1 square equals to 0, so this will be also equals to 0. So here this minus this will be equals to 0. So here omega n you can find out by putting omega n2 with in the place of omega, okay. So here you will get this expression. So only you need to remember this one and this one, okay. So some competitive in competitive examination, so you will be directly getting this type of question, that what will be the natural frequency for a 2-rotor system under undamped free vibration, okay. So you need to say that this is 0, first natural frequency is 0, and second natural frequency is this one kt I1 plus I2 and divided by I1 I2, so which will be under root, okay. Whole thing will be under root. So one of the 2 natural frequency of the system is therefore 0, okay, understood? So while you will be putting omega n1 equals to 0, so from this equation, so what you will be getting actually, so you will be getting this beta 1 by beta 2 ratio as plus 1, okay, plus 1. So this is the mode shape, okay. This is a first mode shape, first principal mode of vibration, omega n1 equals to 0, okay. So in the linear vibration case, so there was some value, okay, omega n1 was some value, was having some value. Now here it is 0, and for this 0 value, so this first ratio, first principal mode of vibration will be plus 1, or this will be the first mode shape, okay, and the second mode shape will be minus I2 by I1. So how you will get this one? So when you will be putting omega n2 equals to this value in either of these ratios, okay, if you replace this omega by this value, so you will get this is as minus of I2 upon I1. Okay, so this is actually often asked in the competitive examination. Okay, so you need to just remember this one. Okay, very actually just actually you need to write it, okay, very distinctly in your copy, okay, so that you do not forget minus of I2 upon I1. In the option you will get plus minus I2 upon I1, plus I2 upon I1, or minus I2 upon I1. So the correct answer will be minus I2 upon I1. So here it is written, the mode shape corresponding to omega n1 equals to 0 is such that the shaft does not twist at all. Okay, so here when omega n1 will be equals to 0, the shaft does not twist. Okay, so you can also feel that thing. So if there is no natural frequency in this shaft, so will the shaft will twist? It will not twist, isn't it? Because they will actually move in the same linear angular velocity. Okay, so there will not be any natural frequency, there will not be any twist. Okay, so that is what actually it is written. Okay, so the mode shape corresponding to omega n1 will be equals to 0 is such that the shaft is not twisted at all. Okay, so vibration cannot take place at this situation. Okay, so in this first situation the vibration cannot takes place. So how actually you will be elaborating the system when omega n1 will be equals to 0? So when a natural frequency, or when a two rotor system will be oscillating with its first principal mode of vibration, then there will not be any kind of vibration. Okay, and the shaft will not be experiencing any twisting. Understood? So this actually denotes that conclusion. Okay, so this is all about your 2-degree freedom system. Only the simple cases we are actually studying. Okay, and which is actually in your syllabus. So now we will be moving towards a new thing, that is vibration isolation. Okay, vibration isolation and transmissibility. Okay, so here this word vibration, I think you are not able to see. Okay, so this is vibration. This is actually while I was doing the stapling. Okay, so it was actually just merged in between these two pages. Okay, so vibration isolation and transmissibility. So what do you mean by actually isolation? I think my voice is audible. Raktim, Bhaskar, anyone please respond. My voice is clear or not?
Yes, sir, it is audible.
Okay, clear now.
Yes, audio.
Okay, okay, thank you. So what do you mean by isolation? So isolation means any undesirable thing if we can somehow isolate, okay, from the system. So that is isolation, isn't it? So there are basically two types of isolation. So one is the motion isolation, another is the force isolation. Okay, so this force isolation is what is called as transmissibility. Okay, and this motion isolation is what actually? So this motion isolation basically due to some delicate instruments, okay, which is in the actually vibratory machine, okay, in the machine, so which may be subjected to certain vibrations actually. Okay, so actually the high speed engine and the machines when mounted on foundations, because the machineries, heavy machineries are mounted on foundations, isn't it, and supports, so they will cause vibration with excessive amplitude. Okay, so why they will vibrate? Because of the unbalanced forces, isn't it? The unbalanced forces set up during their working. Okay, so when they will work, the unbalanced forces will set up. So these are the disturbing forces which will damage the foundation. Okay, so the vibration transmitted to the foundation should be eliminated, isn't it, or reduced considerably by some devices. Okay, so the some isolators are basically used. So those are actually rubbers. Okay, rubbers, those things are written here. You can see some isolator devices are are rubbers, felt. Okay, felt, cork, okay, springs, those are all isolators. Okay, So a cork actually it can withstand compressive load. Okay, so felts they are having high zeta value. Then rubber actually they are shear loading, they can withstand shear loading. Okay, so some high temperature gasoline oils are also used for this vibration isolation. So these devices isolate the vibration by absorbing some disturbing energy themselves and allow only a fraction of the energy to pass through the foundation. Understood? Because whatever excessive energy or excessive force which will generate inside the machine, so it needs to transmit to the ground, then only the vibration can be isolated. Okay, so we need to do the force transmission. Okay, now we will see what is actually this force transmissibility, okay, or force transmission. So what it is actually, so this force transmissibility very important. Okay, so this force transmissibility, so isolation part I have already elaborated. So what is actually force transmissibility? So we need to actually transmit, okay, the excessive force which is generated inside the machine to the ground, okay, or through the support. So it is defined as the ratio of the force transmitted to the foundation to that impressed upon the force. So if I will ask you what was the force which was impressed upon the system in force vibration, will you be able to tell me? So it is F naught sine omega t was the impressed force which was acting on the system while we were studying the force vibration, isn't it? So the ratio between the force transmitted means now we are going to find out the transmission force, okay, the value of the transmission force, because we have to know the ratio. That transmission force divided by the F naught force will give you this force transmissibility ratio. Okay, so this is basically a ratio, force transmissibility. So for that actually what we will be doing, so we will be again this depicting the same concept, okay, so which actually we studied in the force vibration part. So imagine a mass m supported on the foundation by means of a isolator having an equivalent stiffness and damping coefficient k and c. So how we will assume that one? So by this diagram you can see, okay, already we have done, okay, this part in the force vibration, but here this is in the reverse direction, isn't it? Now this is opposite diagram. So here actually what it is said, so a mass m, so mass is remain same, it is mass. So earlier the spring was on the upper side and the damper was on the upper side. Now here it is in the below side. Okay, so actually no change of this diagram, so that thing also happen, no problem, because for a motor vehicle, so if you consider the mass to be this one and this will be your suspension system for an automobile, isn't it? So just like that actually we have drawn this diagram. Okay, so here this isolator having an equivalent stiffness and damping coefficient k and c. So here it is actually assumed that this is an isolator, okay, where the stiffness is k and damping coefficient is c. Okay, so now under steady state force acting on the system can be represented by means of vector diagram, isn't it? Because this is the same diagram which already we have studied. So for this force analysis, for the force analysis, okay, under the steady state vibration part, so we will be again drawing the same diagram, okay, which we have already done in the force vibration. I think all of you have remembered this diagram, okay, how to draw it. So this is x, this is f naught, okay, so they are having one phase angle phi, and this is the spring force kx, and here it is the m omega square x, okay, inertia force. And here perpendicular to this inertia force, you can see this is perpendicular damping force, okay, c omega x. Okay, now one thing you tell me that what are the two forces which are actually directly related, directly connecting this ground. Okay, you can say that this is the ground and the mass. So only the spring force and the damping force. So these are the two forces which basically actually connects, or which are actually generating on this isolator, because now we are considering that this is the isolator and where there is an equivalent stiffness k and equivalent damping coefficient c. Okay, so for this isolator, so these are the two forces which are directly connected, okay, in between this mass of the system and the ground or the support. Okay, so whatever be the excess forces generating here, so we need to transmit those force to the ground. Okay, so we will be finding out the two forces, and here in the diagram you can see that this kx, okay, force is perpendicular to this c omega x, means damping force, because this is related to velocity and this is related to displacement. This is kx and this is c omega. Okay, c omega x, or what you can say. Okay, so this is the perpendicular force. So from this vector diagram you can see. Okay, so this will be the magnitude of this transmission force. Okay, so transmission force, or we need to transmit that amount of force which will be generating due to this spring and this damper. Okay, so how we will be actually finding out the transmission force? So f of tr will be simply equals to what? Kx, this spring force whole square, and this damping force whole square. Okay, so after this drawing this one, actually this diagram, this triangular right angle triangle, so this is x, this is f naught, and obviously this f of tr will be less than this f naught, because here f naught, what was that? This was the total summation of the forces, isn't it, the external forces. So this f of tr cannot be greater than this external force, so this will be having some lower value. Okay, and we need to transmit this force to the ground, isn't it? So this will be simply equals to d square into plus d square. Okay, so here f of tr will be simply under root of this spring force square and this damping force square, and from here if you just take x common, so you will get this one, k square plus c omega square. Okay, now what I will be doing, so I will be putting the value of x. If you just remember the value of x from the force vibration analysis, so it was how much? F naught under root k minus m omega square plus c omega square, if you can remember from the force vibration analysis. Okay, so directly I am putting, instead of x, f naught divided by this one under root k minus m omega square whole square plus c omega square, and this under root k square plus c omega square is already here. Okay, so this one is the expression. Now what I will be doing, because the force transmissibility is the ratio, this is the tr, force transmissibility, okay, is the ratio between the transmitted force to the impressed force. So f of tr will be transmitted force, and f naught will be what? This is the impressed force. Okay, so f of tr divided by this f naught, you can see here it is the f naught. Okay, so if you just remove it in the numerator denominator side, so you will get this ratio. So here the ratio will be what? K square plus c omega square, which can be written as 1 plus 2 zeta omega upon omega n whole square plus 1 minus omega by omega n square whole square plus 2 zeta omega upon omega n square. Okay, so this is already we have done in the force vibration analysis and in the vibration due to support, okay, thing. So already we have done lots of things, okay, for these replacements, isn't it? So this is the very important ratio, and this tr is the transmissibility. Okay, so here this tr is called as transmissibility or force transmissibility. So you need to remember and you need to write all these things, because see, in each of the term or expression, or in each of the term, so you will get this type of expression. So somewhere this square will not be there, somewhere this one will not be there, so you need to remember each and every the term transmissibility, whether it is steady state amplitude, okay, or phase lag, so everything you need to write in a fresh paper. Okay, you need to paste it on your reading table, in front of your reading table, otherwise you will be forgetting, or you will be, okay, this one. So okay, so that thing you need to remember actually. Then again you can find out the phase lag, because this f of tr, okay, transmission force, which is having lower value than the impressed force, so there will be some angle, okay, in between these two forces, so that for that angle is basically this is phi minus alpha. Okay, so phi minus alpha will be what? So this will be phi minus alpha. So alpha will be tan inverse c omega x upon kx. All of us know this thing. And then phi minus alpha will be this minus this one. Okay. So the angle through which the transmitted force lags the impressed force, so can be seen. Okay. So by this angle. Understood? So I think up to this much you need to study for your force vibration. Okay, so it is already over. Okay, this force vibration part is already completed. We have completed. Now only one module is left, but before that, so we will be practicing, okay, some numerical problems, then only your things will be clear. Okay, I think now you have a session by Dr. Buljit Buragoy sir, isn't it? Yes, students.
Yes, sir.
So my screen was visible when I was elaborating. Yes or no? So then why you actually did not respond that time? Now when I actually open in my laptop, so there is nothing actually, nothing it is shown.
Sir, দেখাই আছিলে sir.
Okay, okay. So I think few minutes okay, few minutes earlier I think the screen was actually lost, isn't it? So are you able to understand actually what I wanted to actually make you understand? I will be sharing, okay, the PDF files for today's lecture. Just you go through it. If you find any problem, then if necessary, then again we will be meeting for this lecture. Okay, means for this PDF file, whatever I will be sharing. So again, I will be discussing. Otherwise, see, to miss those things, so you will face problem in the exam. That is the thing. Hmm. Okay, then just wait. Okay, I will be taking your attendance. You are only 14 here. Hmm. Why you are not attending the classes? Okay, thank you. You can leave this meeting.
Thank you, sir.
Yeah.
Thank you,
Thank you.
sir.